This video is about matrices. Now, some of you will have done matrices already, and you can probably fast forward through this video. Others, if you haven't met matrices, then it's important that you do know how to operate with them. Well, the first thing is, what is a matrix? A matrix is basically a rectangle of numbers. I could take the matrix 3, minus 1, 1, 4, 2, 3. That has 2 rows and 3 columns. 2 rows, 3 columns. And we say that the size of the matrix, or the order of the matrix, is a 2 by 3 matrix. Number of rows, number of columns. So if we take the matrix minus 1, 2, 4, 1, 3, 2, 1, 1, that has 4 rows, 2 columns. It's therefore a 4 by 2 matrix. You can have something like this, minus 1, 2, 3. That has 3 rows and 1 column, so that is 3 by 1. So very simple thing to write down. And just the same as when we met complex numbers, which were new to us, we had to make up rules as to how we were going to combine them. We do the same with matrices. What do we mean if we talk about adding 2 matrices? So let's make up some rules to do that. Adding and subtracting. Suppose we have 3 minus 1, 2, 1. Add 1 minus 2, 4, 3. Now this we do in what I might describe as a fairly common sense way. We just take the common elements there. They're both in the first row, first column. So the 2 corresponding numbers and add them. 3 plus 1 gives us 4. Minus 1 plus minus 2 gives us minus 3, and so on. So if we do that, 3 plus 1 is 4. Minus 1 minus 2 is minus 3. 2 plus 4 is 6. And 1 plus 3 is 4. So we add them in a common sense way. That is no property that's sort of absolute in matrices. We say that that is what we mean when we put down one matrix and add another. It's a definition of what we mean by adding. Subtraction comes the same sort of way. If we can keep the screen in one place. If we take 7 minus 1, 2, 3, 1, 1, and we subtract 2, 1, 3, 1, 4, 2, exactly the same idea. Take the corresponding numbers, and that means we take the 7, take away 2, minus 1, take away 1, etc. 7 minus 2 is 5, minus 1, take away 1 is minus 2, 2 minus 3 is minus 1, 3 minus 1, bottom row now, is 2, 1 minus 4 is minus 3, and 1 minus 2 is minus 1. What happens if we do this? 3, 1, 2, 4, plus 2, 1, 1, minus 1, 2, 2. What's that going to be equal to? Well, we can do 3 plus 2, 1 plus 1, and then we have a problem. We cannot add 2 matrices unless they are the same size. So this one cannot be done. They must be the same size, same number of rows and columns for addition and subtraction. Can't spell, and that's no surprise. One more thing that we can do by common sense, we can look at the idea of multiplying a matrix by a number. If I do 3 times 7 minus 2, 2, 4, that will give me 3 times 7. If we just use common sense now, we define what we mean by multiplying in a common sense way. 3 times 7, 3 times minus 2, 3 times 2, 3 times 4. So that is 21 minus 6, 6, 12. So basically, for all of these things, we've just made up rules. And this, when we have these rules of algebra for matrices, then we can go on to use them and do things with them. What happens when we come to multiplying matrices? Well, in this case, we cannot make up a rule for multiplying based on what you might think of as common sense. The rule that we are going to get, if you've not met it before, seems initially quite complicated, but once you get used to it, it's really quite easy. The two matrices I've got written down there, 2, 3, 1, 4 minus 1, 2, times 1, 1, 3, minus 1, 1, 1, 2, 0, minus 1. This now is how we multiply them. If we want to find out what is going to go in the first row and the first column of the new matrix, so when I'm multiplying these, I am looking to see what number am I going to put in the first row and the first column. Let's just get rid of that, change the color. The rule is this: we take the first row of the first matrix. We then turn that row into a column. So that's quite easy to see. You take that first row and make it a column. Having made it a column, then you put it next to the first column. So we have what I would describe as the first row times the first column. Then we do 2 times 1 plus 3 times minus 1 plus 1 times 2. 2 times 1 is 2 plus 3 times minus 1, 2 minus 3, plus 1 times 2, so that's 2 minus 3 plus 2, and that gives us 2 plus 2 is 4 minus 3 is 1. So my first number in the new matrix is going to be 1. Right, now let's look and see. I always like to work along the top row of my new matrix. I've got this one. This number was in the first row and the first column. The next number that I want to look at is in the first row and the second column. So I already have the first row of this matrix turned on end, and I multiply that by the second column. So the number in the first row and second column is the first row turned on end times the second column. Same trick, 2 times 1, 3 times 1, 1 times 0, 2 plus 3, add them together, and we get 5. To find the number at the end here, that number is in the first row and third column. Same trick. We take the first row and multiply it by the third column. 2 times 3, 6. 3 times 1, 3 makes 9. 1 times minus 1 gives us 8. We've now got to this stage, and you can see there's a very good reason why we can't have a number here. That would be in the first row and the fourth column. You cannot have the fourth column. You can't have the first row times the fourth column. There isn't one. So we have now run out of possibilities. So we've finished the top row. We'll put a bracket to show that we've stopped, and we'll get rid of this. Right. Now, let's look at this one. This is in the second row, first column. So we're going to play the same trick. We're going to take the second row and stick it on end. So the second row, stick it on end, will give us 4 minus 1, 2. 4 times 1, 4. Minus 1 makes 5. Plus 4 makes 9. So we get 9 there. Oy, I wanted to write a blue 9. Take this and move it along. And now we're in a position to work out this number, which is the number in the second row and second column. So it is the second row turned on end times the second column. This gives us 4 minus 1 plus 0. So that is 3. And moving it along to the end, we get 4 times 3, or we would do if I didn't lose it. We get 4 times 3 is 12, minus 1 is 11, minus 2 is 9. So that is multiplying two matrices together. Not difficult, but you do have to remember what you're doing. The one thing that should be fairly obvious from that is that if we are multiplying two matrices A times B, the answer will only exist if the number of columns of A must be equal to the number of rows of B. If we don't have that, we can't take the first row and put it next to the first column. The number of columns there must be the same as the number of rows there. What happens now if we think a little bit more about multiplying matrices and we think about changing the order? Of multiplication. It's a very complicated process, so we shouldn't expect nice things necessarily to happen. We know that 3 times 4 is the same as 4 times 3. But does that mean that when I multiply two matrices together and change the order, that they should still be equal? Well, let's have a look. Let's suppose that we have the matrices A times B is equal to minus 1, 2, 1, 3, multiplied by 1, 4, minus 1, 0. Well, doing what I've just done, if I want the first number, that's in the first row and the first column, that is the first row times the first column, minus 1 times 1 plus 2 times minus 1 gives us minus 3. And for the next number along is in the first row and the second column. So the first row times the second column is minus 1 times 4 plus 2 times 0. Minus 1 times 4, 2 times 0. The second row, first column, 1 times 1 minus 3 is minus 2. And the next one is 1 times 4 plus 3 times 0 is 4. So there's the matrix AB. Let's look at the matrix BA. If we just change the order round, we get 1, 4, minus 1, 0, times minus 1, 2, 1, 3. And if we do 1 times minus 1 is minus 1, plus 4 is 3. So we can already see that it's not working. We'll finish it off just for the sake of it. We get 1 times 2 plus 4 times 3 is 14. Minus 1 times minus 1 plus 0 times 1 is 1. Minus 1 times 2 plus 0 times 3 is minus 2. So in general, we cannot say that AB is equal to BA. There will be some matrices where that works, but you cannot assume it by any means. This is all to be found in your textbook, FP1, on pages 73 to 82.